Good morning, everyone. Our today's topic is microwave spectroscopy, the rigid diatomic molecule. Myself, Dr. Jay Sheila, Associate Professor of Physics, Fatima College, Madurai. Let's start from microwave radiation. Microwaves occupy the spectrum from 300 MHz to 300 GHz with wavelengths from 1 meter to 1 mm. The types of rotational molecules are linear molecules, symmetric troughs, asymmetric troughs, and spherical troughs. For linear molecules, the example are CO and HCl. For symmetric troughs, let me take the example is NH3 and CH3Cl. For asymmetric troughs, let's go with H2O. And for spherical troughs, let's go with CH4. Classification of molecule. So for the linear molecules, as you all know, atoms are arranged in a straight line. The example might be HCl or OCS. The three different kind of rotations are possible in this kind of linear molecule. The first rotation about the bond axis. The second rotation of the molecules are end over end rotation in the plane of paper. The third one is end over end rotation at right angles to the plane of paper. So there are three kind of rotations of possible in the linear molecule. Therefore, here the moment of inertia Ia is 0 because of the rotation about the bond axis is easy to rotate. So completely the moment of inertia is 0. But for other two kind of rotation, there is some moment of inertia that might be almost equal. That's only we are taking IB is equal to IC for linear molecule. Next, we may go with symmetric top molecules. As you all know, for symmetric top, we can go with CF. Bond axis might be the main axis in methyl fluoride. So the rotation about the axis also has to be considered. But here, Ia, which is not equal to 0, little bit of moment of inertia can be expected about the bond between CF. So main example for symmetric top molecule is methyl fluoride, where we have the kind of the above mentioned rotations. Here, the value of IB, which is equal to IC, which might be equal to Ia also. But here Ia, which is not equal to 0. But in linear molecule, we found Ia is equal to 0 for easy rotation. Next one is the spherical top. So for spherical top, we can go with the CH4, one of the important example for spherical top. So here the molecule has all three moment of inertia are identical. So here Ia is equal to IB is equal to IC. Then asymmetric top molecule, here you may go with some other example, that is H2O and CH2CHCl. Here overall, when you look at the molecule, so completely the bond might be different. So here Ia, which might be not equal to IB, not equal to IC for asymmetric top. So this is completely opposite to the linear molecules. Next, we may go with a rigid diatomic molecule. One of the best example for the rigid rotator, where we are going to have the two atoms, one is A and another one is B, which is having some distance between A and B. So the mass of A might be considered as M1 and mass of the B atom is considered as V2, M2. The distance between these two masses can be taken as R0. Two atoms might be R0. And the point about which the molecules can rotate might be taken as C. So from the axis C, so the distance between A and C might be taken as R1. And the distance between C and B might be taken as R2. So from this determination, we are going to find out what might be the value of R1, what might be the value of R2 can be calculated, and also what might be the moment of inertia about the axis C. As you all know, a rigid body, which can be defined as that body which does not undergo any change in shape or volume when external forces are applied on it. When forces are applied on a rigid body, the distance between any two particles of the body will remain unchanged, however large the forces may be. Actually, no body is perfectly rigid. Every body can be deformed more or less by the application of the external force. The solids in which the changes produced by external forces are negligibly small might be considered as a rigid body. So again we are starting from the above picture shown, from where we are going to have the distance between the two atoms might be taken as R naught. So here R1 plus R2 might be considered as R. So almost the range M1 R1 can be equivalent to M2 R2. Here as we mentioned, M1 M2 are the masses of two atoms. So from equation 1 again, we are calculating what is R1. R1 is equal to R minus R2. So from this easily we can calculate the value of R2. R2 is equal to M1 R1 by M2. So that can be substituted in the previous equation. So from there we can find out what is R1. R1 is equal to R minus M1 R1 by R2. So basically any type of, whether you can calculate R1 or R2, and also capital R also can be calculated. So from this overall small r1 is equal to capital R divided by 1 plus M1 divided by M2. So from this basically we have the formula for moment of inertia. I is equal to M1 R1 square is equal to M2 R2 square. So we are going to substitute what is the value of M1 R1. So for M1 R1 already we could identify M1 R1 is equal to M2 R2. So that we are substituting M1 R1 here. And also M2 R2 is equal to M1 R1. So in the second we are substituting M1 R1. So commonly if we take M1 R1 outside, so within the bracket we may have R1 plus R2. So from this, easily we can calculate I is equal to M1 M2 divided by M1 plus M2 into R square after substituting R1 and R2 values from the above slide. So overall we are getting this answer for moment of inertia. So the bracket values M1 M2 divided by M1 plus M2 can be taken as mu. So mu can be considered as, what is mu? Mu is the reduced mass. So basically for the kind of exposure, for the kind of the rigid body rotation, we have to take the microwave spectra. The molecules has to be rotated in a proper way. So the classification we could find out, there are linear molecules and symmetric top and asymmetric top and everything. For each we could find out overall the values of the moment of inertia. So here basically when a molecule, the kind of molecule which we have explained, or exposed to microwave radiation, it can absorb energy if the radiation frequency matches the energy difference between the rotational energy level. That is the concept. So for a rigid rotator molecule, the value of Ej might be considered as Vj of j plus 1, where Ej is the rotational energy, can be calculated from J. J is the rotational quantum number that may start from 0, 0, 1, 2, etc. And B is the rotational constant. So for this, what kind of transition can be applicable? That also has to be seen. So here del J is equal to plus or minus 1. So basically it may start from plus 1 to minus 1. So the selection rule can be taken as del J is equal to plus or minus 1. So this can be applicable for all the kind of molecule. So all molecule has to be rotated as per the rotation, only the transition and rotational energy can be calculated. So the energy levels of diatomic rigid rotator. So how we have to find out the energy levels of a diatomic rigid rotator, which is very much easy. So from one of the equation, that is by solving the Schrodinger wave equation, can be given by h square by 8 pi square I j into j plus 1. So here h is a Planck's constant, I, as you all know, that is the moment of inertia, and j rotational quantum number, which may start from 0, 1, 2, 3. So mainly in microwave spectroscopy, the position of rotational lines are usually expressed in per centimeter. So, and hence it's convenient to express rotational energy in per centimeter. So, which can be taken as epsilon j is equal to Ej by Hc. So, overall, that can be identified as epsilon j is equal to V of j into j plus 1. So, here, when we substitute j is equal to 0, so what will come? That may come as 0. So starting from 0, you have to start the spectrum. Then when you apply j is equal to 1, so what will come? So within the bracket 1 plus 1 is equal to 2. So 2b. So for j is equal to rotational quantum number, j is equal to 1. The value of epsilon j, rotational energy, which may come as 2b. So the second level is 2b. So when you are applying j is equal to 2, what will come? So 2 plus 1, right? 2 plus 1. So there also 1, 2 is there. So accordingly, we can have the levels in the spectrum for the rigid rotator, right? Diatomic rigid rotator, we can have the spectrum like this. So for each value of the rotational quantum number, j is equal to 0 and 1 and 2 and 3, yes, that may go on increasing the energy level. But for non-rigid rotator, in the beginning portion, in the lowest energy level, almost the spectral lines are equal, up to almost 4, that might be equal. So when it starts from the level 5, so there is a transition, that is the lower shifting can be expected from the upper shift of the rigid rotator because of the elongation of the non-rigid rotator. So now you could understand the classification of molecule, what is the microwave radiation, how the microwave spectrum can be identified, how the spectrum can be taken, and especially for a rigid diatomic molecule, how the spectrum can be formed, and how the moment of inertia also can be calculated, and everything you could understand, I think. Thank you all.